today. All right, before I start, this is a disclaimer. The concept now is we're getting into inferential statistics a little bit today. And some of these ideas, some of this thinking might be abstract a little bit for you. So what I'm hoping you'll do, and I'm going to try to help with that. I'm going to try to do a little bit of some practical stuff with it to try to make it make more sense. But if you find yourself lost, it's all right, because we're going to stay with these same set of concepts for the next 2 weeks after this, right? So today it's going to seem like it's foggy. Next week it's going to seem a little bit more concrete, and by the time it ends, you'll be like, hypothesis testing is easy. All right. So again, if you feel lost, don't worry about it. We all did. This is so. Just sit back. You know, just let your mind run free. If you have any marijuana, please take that. That'll help. Because I don't want you to get feel like you're behind. All right. So I'm gonna start with the homework, just real quick.
I don't think this is going to work.
And again, if I don't have your homework yet, it's okay. Like I am keeping track, like when I get it, I just mark it. Yeah, I got it. And but I don't really care if you didn't get to it, no problem. I want to kind of encourage you to practice and try and struggle. Stuff like I had a help session on Wednesday for Natasha, and Marianne showed up. I'm thinking because Natasha asked me, she was having some trouble. So I'm thinking of maybe, Wednesdays at 9 a.m. What time is that in Colorado? Like 4 in the morning?
It's not that bad.
That's not too.
It's 7.
7. Isn't
Yeah,
it?
maybe that's a little bit too early for you guys, but coming up with like a 20-minute, half an hour help session,
Mhm.
as we continue to build on this math practice thing. And I think we accomplished quite a bit, So the homework, if you look at this, my weight here from the nice, neat bell-shaped curve. The first time, that's the whole population with my, with my weight being, the mean being 184 pounds, the average. The median being 185 and the mode being 186. That tells me I have a normal bell-shaped curve, right? Because those three things are on the same line, around 184, 185, right in the middle there, right? And then when we did the sample, a little bit different now, right? Now all of a sudden, it's skewed to the right. And let's think about why that is. So let's say, look at, now that was the year, those 2 years were the year where I was like, man, I was starting to get lightheaded and stuff. Maybe working too hard, traveling too hard, whatever. I knew I got to get things right. So there was that huge swing from 199 pounds to 178 pounds just in those 2 years. All right. So I got, and also, if you look at the standard deviation during that time, before, for all of my weights up until today, the standard deviation was about 4 pounds. So my process is getting, over time, has gotten more stable, right? More under control. But back then, my standard deviation was about 6 pounds. That's the amount that it varied away from the average. And then, so you can see where, if you look at this smaller curve, the second one, which is the, those 2 years, my mean's at 187. So you look at the top of the peak there of that graph, that's 187. But my median, which is the middle number in that 2 years, is 185. So that's different than 187. I just got to tell my wife I'll call her later. She forgot I was having fun. And then the mode, which is the one that occurs most often, is 182. So, and again, in a normal curve, that first one we drew. And how do we get to a normal bell-shaped curve? Anybody?
Add more data.
Who's that? Jack? Who was that?
Yep.
Exactly. Add more data, right?
Provided the process is normal.
Stable. It's under control. So the only thing that's going to happen now is special causes of variation, right? I broke my ankle. I couldn't run, for 3 weeks. That would be a special cause, right? Because as long as my process is in control, the more data I have, the nice and clean and neat my bell-shaped curve becomes. All right. So that was the homework. And then just a quick review on how to get that data point, data analysis package. It's right here under if you data, once you get it, and you can go file, go down the bottom and hit options, click on add-ins. And mine's already installed, but you click on it, it'll be down here in inactive application add-ins, double click it, and then just make sure you hit OK. And then reboot Excel, and then go to your data and it should be there. And if not, we're gonna figure out, we'll get it for you. We'll just do a quick session. Anytime you guys want, say, hey, send me a note, an email. Hey, Bill, can we get together for 10 minutes, 5 minutes? I'll do it. I might be in a meeting or something or whatever, but I will definitely, we can do it quickly, okay? Today, so that's descriptive statistics, from our measure phase. And the two things that we're interested in are two types of data, right? One is central tendency, like what's our averages, what's our median, and what's the mode. That tells us central tendency of this data. Just keep in mind as we go through this, the analyze phase, which is next, data does not talk. It just lays there. It doesn't tell us anything. So we need to pull information out of it that we can make decisions with. So one is central tendency and two is variation. And that's where we see things like standard deviation. And then part of descriptive statistics is all of the graphing that allows us to see what's going on with data also, right? And now today we're going to talk about, I'm just going to just quickly go to this one, inferential data. We're going to get into this in a little while. But this is about how do we make inferences or guesses, hypotheses about data. The one we're going to go through today is about the average temperature in Connecticut in July. And it could just as easily been with this set of data. One hypothesis might be Bill's weight is significantly different during the holidays than it is the rest of the year over the last 16 years. All right, and maybe I want to know that. Maybe all of a sudden I get like the Michelin Man come Christmas time, around Thanksgiving and Christmas. All right. So those are the types of things when we talk about inferential statistics. Those are the kinds of fun things that we can pull out of our data with another set of tools. Now, I wish that I could tell you that these statisticians, I really want to make things simple for us. All right. But they make it very complicated. So my job as a teacher always is to make things that seem complicated as simple as possible. So that's my goal today. And I know I'm not going to accomplish it 100%, but I'm going to try to get close. All right. So let's start down the road of the analyze phase. So you're 2/5 of the way to the green belt, which is you're going up the pyramid, not that easy, but we're 2/5 of the way there. And again, just a review, define, what are we doing? Define the problem and the objectives. What's the problem here? I guess is the right question. The measure is helps us really understand better what our problem is. What do we need to improve? Can we measure it? And now we're into the analyze phase, where we're going to take all that data and be able to make it talk. Because right now we just defined and measured, and we got like a whole bunch of measurements. Now what? And then obviously in the future, we get over this hump called the analyze phase, and we get into the fun parts, which is the improve and the control phases. So analyze is about finding the top 1 or 3 causes, right? Remember when we talked about that formula back in right at the beginning, y is a function of x. Like in other words, my output is going to be a function of 2 or 3 or 4 variables, x's, any process, right? But think about my weight for a second. My weight there's a whole bunch of x's that go in that. My diet, my exercise, my sleep, whatever. But generally it's it's called a vital few factors, so 1 to 3. We're not looking at 20. We just got to figure out what those 1 to 3 are, right? And that's kind of what we do in this analyze phase. So we might look at a whole bunch of potential causes, and then we use a whole bunch of these tools in the analyze phase to figure out what are our vital few factors that are impacting our process. And is the process doing what we want it to do? And by identifying these 1 to 3 causes, we can get our process to do what we need it to do, control. So today, I'm going to show you a tool, a way that makes data talk called multivariate analysis. I'm just going to show it to you. You know, it's something that you probably put on the back burner, maybe use it at some point, but it's a way to look at many variables at the same time and get some direction in terms of what it's saying to us. We're going to talk a little bit about classes of distribution. We're familiar now with a normal distribution. That's what we did with my weight, but there's others depending on what kind of data we have that we might use, okay? And then we get into the fun part, the inferential statistics, understanding inference and sampling techniques. We're going to get into some, putting our toe in the water for hypothesis testing, like the basics, general concepts, significance, risk, types and decisions for hypothesis testing, reading tables. And I think we're going to probably stop there. And then next week, we're going to get into a whole bunch of different types of hypothesis tests. And then the following week, we're going to get into a whole bunch of different types of hypothesis tests. So I'm warning you, there's like 50 of them. We're not going to go in depth, maybe 2 or 3 that you may use in the future. And that's the analyze phase. So let's talk first about patterns of variation. And particularly this real cool tool called multivariate. It's another type of a graph, but it shows patterns of variation, many variables. And the variables can exist within a subgroup, between subgroups over time. And there's 3 classifications for variation source. One is positional, cyclical, and temporal. And this is not on the exam. So again, this is where you just kind of sit back, relax. Positional is when I see variation inside the same unit, all right, and within the same part. You know, it might vary dimensionally like this block does, all right? Could be a single unit, could be location in a batch process like plating or something like that, but I see variation within the same unit. And then cyclical is between units, consecutive pieces, groups of pieces, consecutive batches. And again, in the molding process, maybe this would see some cyclical variation. And also, you know, if I don't get the same part, same way every single time, I may see positional variation. And then third is temporal, which means I see a variation shift to shift, day to day, week to week. All right. And just quickly, I want to kind of give you an illustration of why I might use the multivariate chart. In this scenario, let's pretend my wife, she sold her frozen yogurt shop back in August last year, but let's say she had it still, and she was thinking about buying another one, which I think you'd have to have rocks in your head. But there's a couple of variables that might help us make a decision about where and what size store to make. And we want to look at store size and store location and how it impacts profit. So multivariate chart, basically, if you look at the bottom, I may look at 3 different store sizes. Those are down the bottom, store size. I might look at 3, 4 store locations. Could be Hartford, could be Southington, could be like Townsend, you know, around the Hartford area, whatever location, in plazas and, you know, freestanding buildings, the whole 9 yards. And what the multivariate chart does is I chart all of that information on one chart. And then I see a trend line, and I can kind of make conclusions based on what's the right store size, you know, in terms of profit, and the right location. So that's multivariate. I just wanted to give you exposure to it. It gives you a simple plot from sometimes a lot of data. So just keep in the back of your head in case you ever find yourself saying, I wish I knew a tool to do multivariable. And it kind of goes against all of us scientists. I'm a chemist by trade, because generally what we talk about always is single factor experiments. I don't want to change more than one variable at a time, you know, when I'm doing my plan, do, check, acts. But this allows us to look at multiple variables at once. All right. Any questions on multivariate chart? It's not on the test, so. Classes of distribution. And again, we did one. Distributions are ways of looking at data. Which one do we get to look at?
Normal, right?
Yep, normal, right? We saw normal.
Gaussian.
Yeah, based on the fact that we had descriptive, we had data that we can measure, which was my weight. So that's called continuous data. And we also had 16 years worth of it. So I can use normal. And then don't forget, in order to build that, make that distribution, that bell-shaped curve, I had to do a formula, right? Remember? And it was the one in Excel where it was X times the mean times the standard deviation. And then it was false or true. Remember that, to get that distribution? Each of these, depending on what kind of data I have, the normal may not make sense. All right, it may not give me what I needed. So all these other types of distributions come with their own formula. I think that's all I'd like you to take away from this slide. And these are the one that I think I'm really most interested in here. Binomial and Poisson are for discrete data, which is data we what?
Count.
Jack, that's why you're the lean guy in Colorado. Discrete for 500, Bill. Yep. So that's data we can count, and continuous is data we measure. So binomial and Poisson, which we're just going to touch on, are for discrete data, and then student T, which is I think you'll like that one. That's probably one that you may use. Normal, and then the F distribution chi-square. But I'm just going to show you those distributions quickly. So these are the two for discrete data, for data that we count. You know, so think poles. That's how I usually think about discrete data. It's used to model it, right? So it's just like if I wanted to draw that curve like we did for my weight, but my data isn't 16 years worth, and it's not continuous, then binomial might be one where my population is big, my sample size is small, and it might be something like I'm running an experiment several times in a row, flipping a coin 3 times. What's the likelihood of getting head 2 times? That kind of information, right? So that's data that we count. It's not data that we measure, flipping a coin, okay? But I can graph that. And then Poisson distribution is used as a distribution for defect counts. So how many defects do I have in a given part? Is also a good predictor one. It's like how unusual is an event? And the example I'm giving, even though I hate LeBron James because I'm a Celtic fan, is averaging 35 points per game. What's the likelihood he will score 12 points in the first quarter of his next game? By doing a Poisson distribution that has its own formula, I could look at all his data, all his scoring data, and come up with the probability of, again, a pretty good feel for what's the likelihood that he can score 12 points in the first quarter of the next game. All right. And normal, we got that down to a science, right? The total area under the curve is 100, shaped like a bell. It could be skewed one way or the other, depending on how in control my process is. The mean, median, and mode are the same. And we got that one now. This one here, now the student T is the one that is really cool. And the reason I like it is because I can do, if I have a small sample size, and I like the example I like to use is if I want to understand the average weight of polar bears, I'm probably not going to go out and get a large sample of polar bears, right? However, because I'm not getting a big sample, I may get, let's say the average polar bear weighs 500 kilograms. I may get a couple in my sample that are 150 or 100, and I may get another one that's 800. What Student T does is it takes care of the outliers. And this thing was so big when it first came out in the 50s, because it allows me with a small data set to look at a small data set just like we were able to look at with the normal distribution. That's all it does. It converts a small sample size into something that it lessens the impact of the outliers for my samples. Okay. And then the F distribution is used to test for equality of variances from two normal populations. Let me move I put some notes on this one. So let's consider you're testing a new drug for heart disease. You want to determine the significant effects of different dosages. So being the great statistician you are, you set up trials of 0 milligrams, 50 milligrams, and 100 milligrams of X in 3 randomly selected groups of 30 each. And this is a case, where we would use an F distribution. Anytime you're comparing more than 2 groups, and again, in this case, we're looking at groups of 0 milligram, 50, and 100. That's when I would use a F distribution. And then chi-square, I need to estimate how closely an observed distribution matches an expected distribution. Estimate whether 2 random variables are independent. And I think that's all I'm going to say about that. Inferential statistics. Now I'm going to stop sharing. I'm going to go back into math practice, because I think what I want to do, if I take you through these slides, guys, you're going to have to go grab toothpicks to keep your eyes open, honestly, because it's just so abstract. So I'm hoping by going into a real world example and touching on a lot of things we're going to look at in the slides, when we get back to the slides, they'll make some more sense to you. Okay. So this is an experiment. I think I did it in my last class. I think it worked out good. Let's see. You could be the judge by how drowsy you are at the end. All right, so inferential statistics. So again, descriptive statistics, we're looking at tendency, we're looking at, amount of variation. When we get into inferential statistics, now we're talking about, all right, I have the data. What can I learn from it? Like how can I predict what's coming, right? And this is just one example. It is known that the average temperature in July in Connecticut is 87.5 degrees Fahrenheit with a standard deviation of 3.5. So right away, is that, what kind of distribution are we thinking?
Normal.
Right, because it's data that I have, probably 100 years worth. Right, I got a lot of data, way more than 30. And again, and I think the process itself is fairly stable, right? Year to year, if you look at the data, we're not going to see generally in July 20 to 25 degrees here in Connecticut. All right. So the temperature last July 15th was 94 degrees Fahrenheit. And these are the kind of questions when you do inferential statistics that you can ask. Was that day's temperature statistically significantly different than the average for the month of July? All right, that's all you're saying, is it? And what we're going to get into when we get into the slides, what statistically significantly difference mean. So basically, I can come up with a formula, and based on a confidence level of, like, let's say I want to be 90% or 95% confident that 94 degrees was statistically different than before. And again, it might help again to think about my weights. The question would be, during the holidays, Bill's weight is significantly different than the rest of the year. All right. Or the day after Christmas, or whatever the heck you want to do, right? The week after Christmas. But these are the types of things we can ask ourselves instead of just taking data and putting it into our computer, and letting it lay there and sleep there. These are things that we can start to get information from this data that just lays on the page. So I wanted to kind of just introduce you to these 6 steps that I need to do to figure out whether that day is statistically different than the average for the month of July over the last 100 years. All right. And again, these steps are the same steps we're going to be taking for every type of hypothesis test that we're going to look at over the next 2 weeks. They're always the same. All right. So one, I need to come up with I need to define the objective. All right. And the objective, another word for that, because statisticians just love to they're like lawyers, right? They want to make it as complicated as possible. Defining the objective is the same thing as a research statement. It's basically a hypothesis statement. So in this case, I want to clearly define the objective by saying, was July 15th temperature significantly different than the average for the month of July? That's it. That's my research statement. All right, so I'm going to ask a question. Secondly, the next thing I have to understand is, will this question be evaluated using a one-tail or a two-tail test? And all that means is, here, let's say this is the bell-shaped curve for all the temperatures right here. I'm going to put it over this chart. All that means is, if I was asking the question, was July 15th significantly hotter than the average, then I'd only be looking to see if it's on the right side of the chart, right? I don't care about how much, if it's colder. I'm just interested in if it's hotter than normal. That would be called a one-tail test. And then, or if I asked, was July 15th colder than the average over the last 100 years? Same thing. It would be down the other end, down the left side of the graph, right? And I'd only be interested in that side. That would be a one-tail test. But I'm not asking that. I'm asking, is the day's temperature significantly different than the average? So it doesn't matter whether it was hotter or colder. So that's a two-tailed test. All right. And that matters. And you'll see why in a second. Then I'm going to select a test distribution and a critical value. Part of that is, for depending on what kind of hypothesis test you're doing, like in this case, we're looking at a z-test. Just like, remember, this is the formula that we used. This is the formula that we used right here when we did our this data here, like to get this normal distribution. And that formula is right here. It takes that number and, it's the same exact thing, but each of these types of distributions have their own formula. All right, so that's called a critical value. And it's often, all you need to do is go into Google Z table. And for every kind of distribution, you can Google different types of tables, and it tells you what that critical value is. All right. And when I go to look it up, I need to know what my confidence level, what confidence level do I want to look at it with, right? So the confidence level means I want to know if the temperature on July 15th is significantly different than the average for July. I want to be 90% or 95% or 98% confident. All right. And you have to do that first. You can't do it after the fact, because that's going to, when I go into the table to find out what my critical value is, it's going to ask, one of the things that I need to look at when I go into the table is, what confidence level do you want to know? And the most common is 95%. All right. So for this z-test, and for this particular exercise, I've selected 95% confidence. All right. And at 95% confident, what I come up with is a value of 1.96. That's the number that I get, right? And the way it works is, if you look at on the graph here that I drew, this is the average, 87.5 degrees. And right to left is 1.96, right? Plus 1.96 and minus 1.96. All right, so again, we're going to get into over the next couple of weeks how I got that. All right, but for now, and basically, so that 1.96, if you guys see my pointer here, It's almost like I'm putting the goalposts up on both sides, right? So all I'm saying is, after I do figure out what my test, like if I do the math with that 94 degrees, I'm going to put it on my graph. And if it falls to the right of that goalpost on the right, if it's that 1.96, if it falls in that area there, that's called the rejection region. That means I'm going to reject the null hypothesis. Now, there's two. I skipped that, didn't I? Yeah, I skipped that. So I skipped that step. So a null hypothesis is the status quo, which means today's temperature is not significantly different than the average for the month of July. It's always, that's why they call it a null hypothesis. It's almost like innocent until proven guilty. I have to prove that. The only objective in hypothesis testing is to reject the null hypothesis. That's it. And the only way I can do that is if I fall into the rejection region, right? And then the alternate hypothesis is, yes, today's temperature, 87.5 degrees, I'm sorry, 94 degrees on July 15th is significantly different than the average for the month of July. So the null hypothesis is there's no difference. And it's always the same. It's always null is no difference. And the alternative is, yes, there is a difference. And the only objective of all the hypothesis tests you're going to see, fancy formulas, is the only objective is, can we reject the null hypothesis? That's it. All right. All right. So creating this. So now I have a critical value that I took out of a table, which is 1.96 on both sides for a 95% confidence level. And then I have to calculate my test statistic. Let me slide over here so you guys can see it. And here's the formula for z-table, for a z distribution. Bell-shaped curve, normal data. Z is equal to X, which is going to be 94 degrees. That's my statistic I'm interested in. Minus the mu, which is a fancy way to say average, which is 87.5 for the last 100 years, divided by epsilon, which is the standard deviation. And when I do that calculation, it comes out with a number of 1.857. So now I go back to my graph and I take that 1.857. So I know that to the right, the rejection region starts at 1.96. To the left, it starts at minus 1.96. So 1.857, where does that land? Anybody? Does it land before the rejection region, like underneath the curve, or beyond?
Before.
Right? So it would be somewhere probably right here, right? So once I do that, once I got that test statistic and it doesn't fall in the rejection region, all that means is July 15th was not significantly different than the last 100 years average temperature in July in Connecticut. So I failed to reject the null hypothesis. That makes sense? All right, so that's the easy part, because believe me, if I go through the slides and then do this, at the end of it, you'd be like, okay, now I got it. Now I'm hoping that we go into the slides, they don't look like Latin, right? So let's try it. So that's
I understand. Those 1.96s, 95% of the data is between those two, right? That was your
Right.
hypothesis.
That's my 95% level of confidence. And again, you can think about like, for this is optional homework if you feel ambitious, and if you got nothing else going on in your life. But basically, I'd love, if maybe you want to say, hey, listen, let's see if Bill's weight after Thanksgiving, between Thanksgiving and New Year's, is significantly different than the average of 184.6. Maybe we could do it, as weeks go on, we could play with that, but you see the power of it in terms of making data talk. All right, so now we get into this thing again. You see, okay? So we already went through most of the stuff. Now I'm going to be able to fly for the most part. So understanding inference, it's about making inferences regarding the characteristics of an unobserved population based on the characteristics of a sample, right? So the sample would be, in this case, it would be maybe my weights between Christmas and New Year's would be a sample, right? We rely on sample data to draw conclusions. And think about it, that's how we make conclusions in our business, right? We're taking samples of things. We're not looking at the whole population. So I need to know that that sample is representative of the whole population. It's widely used because it's sometimes impossible to collect the entire population. Like if I wanted to weigh polar bears, I'd have to get every one of them the rest of my life. Statistical inference contains two elements. This is kind of the slide I just took you through. One is what is the inference and what's the measure of validity. And those are the steps that we're going to continue to kind of go through. Define the objective or the problem statement or the research question. Decide if it'll be evaluated by a one or two tailed test. Formulate a null and alternate hypothesis. And remembering that the null is always going to be the status quo, right? They're innocent until proven guilty. I have to prove guilt. Well, same thing here. Select a test distribution and a critical value. And that's usually, that goes from a table, depending on what my confidence level is. Then I have to do a little bit of math, calculate a test statistic, and then compare the calculated value to the critical value, and determine if the null hypothesis is to be rejected or not. Now imagine if I did this, I showed you this without like going through that on my own. So the outcome of, or conclusion, is a statistical proposition. So in other words, was 94 degrees, was that day, July 15th, statistically different? It's a statistical proposition about the population, right? There's also practical, like in other words, does it feel a lot colder, you know, or a lot hotter? And here's some examples of statistical propositions. Making predictions is probably the biggest one. All right, let's get into a little bit about sampling because I think it's important. Here's a notation again. You know, we saw these, you will see these in the formula as we go up. This is kind of dispersed throughout the 1200 slides, just a reminder what all these are. So, you know, today we talked about the epsilon here, the standard deviation, the mu, which is the mean right here. Sample size is n, population size is capital N. So we're starting to touch on a lot of these. Today we're going to talk about alpha and beta risk a little bit. So population is the entire set, everything. Sampling is, it's the process of selecting a subset. And it's the reason we want to make sure we're careful when we sample is we want it to represent the entire population. It's impractical to collect the whole population. Yeah, think about the whales again. Lower costs for sampling. That's just common sense. Two major uses of samples. One is estimating the population parameters using the sample, and hypothesis testing, testing a statement about the population characteristic using sample data. And as these statisticians, there's 6 different types of sampling strategies. We'll go through them real quickly. One is simple random. They're selected in a way that each item in the population has an equal chance of being selected. You just go grab a piece and measure it. There's no bias. It's really the basic sampling strategy. Then there's matched random samples. These are samples that are randomly selected in pairs. So, for example, researchers are interested in understanding the weight of twins, or interested in understanding patients' blood pressure before and after some medicine. I have to do those in pairs. And then there's stratified sampling. A population can be grouped or stratified into distinct and independent categories. An individual category can be considered a subpopulation. They're randomly selected in each category. And I think we'll go right to the example. A fruit store wants to measure the quality of all their oranges. So they want to use stratified sampling by region. So about 40% of the oranges come from California. So 40% of the sample is going to be selected from California oranges. That's how stratified sampling works. Systematic sampling, these are selected at regular intervals based on an ordered list where items in the population are arranged according to a certain criterion. But the example would be we're sampling every 5th unit. This is where the AQL, that's systematic sampling, or we're going to take a sample off the line every hour or every 10 minutes or whatever, or every 100th unit. And cluster sampling is a sampling method where samples are only selected from certain clusters or groups of the population. And the example there is selecting samples from the region where researchers are located, so the cost and time spent on traveling is reduced. Sample size, it's a critical element. Again, the statisticians, they like to go pretty deep into everything, and sample size is no exception. There's formulas for what is the right sample size, right? Because the smaller the sample size, the higher the risk that I'm going to have outliers, right? I might have that 100-pound whale or that 350-pound whale. The greater the sample size, the more time and money you're spending. But if I get the right sample size, I can minimize the impact of outliers. And here's the formula for the sample size, how much we should have. The Z-score indicates how much a given value differs from the standard deviation, as you know, from the weight stuff. It's a reflection of the amount of variability within a given set. But if you ever need to know, this is the formula to figure out how many samples do I need to take. And if calculated sample size exceeds 5% of the population, discount using the following equation. For discrete data, which is data that we count, there's the formula, same thing. How many samples do I need in order for it to be statistically relevant? Not on the test. You guys are probably saying, what's on the test? All right. Sampling errors, random sampling error. The random variation due to observations being selected randomly is inherent in the sampling process and beyond one's control. And then selection bias is another type of sampling error where non-random variations due to inadequate design of sampling. It can be improved by adjusting sample size and sample strategy. So all I want you to know from all that is there's a science behind sampling. All right, now we'll get into the fun part. We did our first hypothesis test on the temperatures. So let's go through a review of what that, some different types. There's a couple of really cool, easy videos too. Periodically I'll send you links. Where people all over the world, they try to do what I'm doing, is make some of this stuff digestible. So I'll probably send you a couple of those. But it's a statistical method in which a specific hypothesis is formed about a population. And the decision of whether to reject the hypothesis is based on sample data. And basically, a statistical hypothesis, we're always going to have two statements. One is the null hypothesis, and one is the alternative hypothesis, H naught and HA. And the H naught was there's no significant difference the temperature on July 15th. The alternative is yes, there was. And all we want to do is reject the null. We try to answer whether there is a difference between different groups or there is some change occurring. For example, are the average SAT scores of graduates from high school A and B the same? Is the error rate of one group of operators higher than that of another group? We have a whole bunch of data on first shift and second shift. Is the error rate higher on one or the other? Don't forget, the data just stays in the computer, sleeping. Are there non-random causes that influence the height of kids in one state? Like there's no real end to types of hypothesis you can do based on data set. The null hypothesis states there's no difference in the measurement, no changes occurred, and sample observations result from random chance. Alternative hypothesis states that there is a difference in the measurement of different groups, some changes have occurred, and sample observations are affected by non-random causes. So here's the two possible conclusions. One, reject the null, or two, fail to reject the null. And when there's enough evidence based on the sample information to prove the alternative hypothesis, then we can reject the null. Like, so in other words, if we had, after we graph that temperature, that's test statistic, if we fell into that reject region. I like, guys, you can do it without the graph, but I feel like it just makes it so much easier when you do it graphically like that. I think it's so much easier to see. When there's not enough evidence, then we fail to reject. That's hypothesis in the elevator speech. So let's talk a little bit about, I think I had mentioned the concept of statistical significance of that temperature, right? This is statistically different than the average in July versus practical. So practical significance, it's an observed difference is practically significant when it's large enough to make a practical difference, right? So practically, it could be, if the temperature was 40 on July 50, that's a practically significant difference. A difference between groups that's statistically significant may not be large enough to be practically significant. All right. So just because it's practically significant, when I'm looking at statistically significant, it may or may not be big enough. In statistics, an observed difference is statistically significant if it's unlikely the difference occurred by pure chance, given the predetermined probability threshold. Statistical significance indicates there are some non-random factors causing the result to take place. And in hypothesis testing, statistical significance indicates the amount of evidence which is sufficiently persuasive. You see where your eyes can glaze over? Everybody? Imagine. This is the toughest class, I think. Probability. So maybe shake it up a little bit. It refers to the likelihood, the chance, or a possibility of an occurrence. So the probability of any event lies between 0 and 1. Sum of all the probabilities of all possible events in a sample space is equal to 1, or 100%. And probability is always a ratio, right? And so we talk about, best way to illustrate that is by looking at rolling a die. A die has 6 sides, a dice, like at the casino. So there's a sample space of 6. Each face is unique. Thus, each time a die is rolled, there's a 1 out of 6 chance that will land on any particular number. So 1 out of 6, there's a bunch of different ways you could say it. It's chances are 1:6, 1/6, or 0.1667, which is the same as 16. We have a 16.67% chance that I'm gonna roll a die and get the number, like a number 2, for example. And then the probability of getting 5 1s in a row, right? I'm gonna roll my dice and 5 times in a row, I'm gonna get the number 1. Here's the probability of that. This is how gambling is thought of, right? This is how the odds are determined. So the probability of getting a 1 is 0.1667, and the probability of 5 1s, I'm going to take that 0.1667 and multiply it times 5, so my odds are 0.0013. So I have 1.3 chances out of 1,000 that if I roll a die, I'm going to get 1s 5 times in a row. So calculated probability allows the establishment of acceptable risk, thus gambling. The p-value, the differences between observed data versus claims made under the null hypothesis may be real or due to chance. The p-value is the probability of these differences occurring solely by chance, random. Okay. And this kind of all gets into the idea of the rejection region that we're talking about, confidence level. The alpha level is another way of saying rejection region. Again, these terms are all the same. And it's the threshold against which p-values are measured, right? So I have to have an alpha level and a rejection region are the same. When you hear alpha, think rejection region. The null hypothesis is rejected if the p-value is less than my alpha value, right? So it's less than my rejection region, which is what happened with that temperature. And the most common used levels, confidence levels, are 5%, 10%, and 1%. So 95% confident, 90% confident, 99% confident. And depending on which one you pick, when you go to the table, that's how you're going to get your statistic that you're going to compare your test statistic to, your critical value. All the same stuff. So even risk and alpha and beta, just think confidence level, and think rejection region. There's two types of errors. One is a type 1 error, false positive, false alarm, or alpha error. It's associated with the risk of accepting false positive. It occurs when we think there's a difference between groups, but in fact, there is none. An example would be telling a patient he or she is sick, and when in fact, he or she is not. That's a type 1 error. So it's convicting somebody of a crime when they're innocent. And alpha and confidence level. Alpha indicates the probability of making a type 1 error. It ranges from 0 to 1. So this is all the thinking that goes into the calculations that tell me that 1.96. Okay, that's all I'd like you to know. When making a decision on whether to reject the null, we compare the p-value against alpha. Again, forget that. Like, just think about what I took you through with the temperature. Okay, but it's the same exact thing. It's another bunch of different words. Type 2 error is a false negative, and that's telling a patient that he is sick, and in fact he is. I'm sorry, telling me he's not sick when in fact he is sick. It's the risk of accepting false negatives. So basically, you know, we want our data when we get into hypothesis testing, we want to be pretty confident in what the numbers are going to tell us when we get done looking at them through a hypothesis test. Beta indicates the probability of making a type 2 error. Same thing. Just think rejection region. This slide, which you'll have, you know, when I send you the deck, just kind of gives you types of errors. Okay. The confidence interval, that's the same as the rejection region. It's an interval where the true population parameter would fall within a certain confidence level. 95% is the one that we use most often, most commonly used confidence level. And the width of a confidence interval depends on the confidence level, the sample size, the variability in the data. The higher the confidence level, the wider the confidence interval. And I'm going to skip the rest of it because it's like, what do you call that? Word salad. This is all it means. All right, confidence interval calculations are built into most software. And that's just the rejection region, the little black areas down there. There's a formula there. You don't have to do the formulas because all you need to do is go into a table. All right. And I think we're done. I'm gonna stop here. That's enough, right? It's enough for one day. Whew. I hope everybody was able to stay awake. I don't have any homework, so just if you want to get caught up, unless you want to work through doing a simple hypothesis test with my weight. If so, just reach out to me and we can do it. It's just voluntary, if you feel like it. Have a great rest of Friday. I'll get the recording off.
I had a quick question.
All right.
So it looks like your alpha and beta are, I guess, opposites. So your beta is the confidence and your alpha is the rejection, right? So it looks like either one can be used in any scenario to get the same answer. Is that right?
Correct. It is. And again, I kind of take alpha, Hunter, out of my mind, alpha and beta. And because I am not the smartest tack in the box. I like to think of rejection region.
Okay. Cool.
But yes, you are 100% correct.
So is there any reason you'd use one over the other, or is it just preference? Like what equation wise, I guess.
I need to get back to you on that.
Okay.
I haven't thought through that. Let me write it down. I'll clarify that. I'm so used to just skimming over all that because I'm so simple with rejection region. So I'll get that for you, Hunter. Okay. That's a good one. Any other questions? Stump the knucklehead you're playing. Have a great weekend, people. Thank you so much for
You
showing
too,
up.
Bill. Take care.
We'll see you, Bill.
Yep.